All right, welcome to Chapter 4. This chapter we're going to talk about SIP building science. We could talk about building science for days, if not weeks, because it's that big of a subject. But I've tried to narrow this down into close to a 1-hour discussion on issues that I think are most important for you as a builder or an installer to really understand about building science. And a good portion of this presentation, I have to give credit to the folks at Building Science Corporation. Joe Stebrook is the author of the book, which is Building with SIPs, Building with Structural Insulated Panels. It's a field guide. And I'm strongly going to encourage, if you don't have a copy, to make sure that you do and read that. It's going to be a huge part of your understanding building science to the level that you should understand that. So a lot of the photos that you're going to see come out of that guide, come out of the builder's guide. A lot of what I've learned about building science, I've certainly learned from those folks and working with Joe on this book. And I think it's important that you bring your level of building science knowledge up to a certain minimum level, maybe not the PhD that Joe Stebrook has, but certainly enough to understand how it affects what you do working with SIPs. So what is building science? A simple definition of building science would be something along the lines of a study of the environment, the system, and the people all together in a big melting pot and how they interact with one another. I'm being simplified here, but it's basically, if I'm in a room, how do I feel? How does the room make me feel? What's the environment of the room? And how do we relate to one another? How do I affect the room? How does the room affect me? Everything within a building is a system or a subsystem or a component of a subsystem. And they all do different things to each other, to different portions of the structure and to the people that live in that structure. So in very simple terms, it's the interrelationship of all of these various things inside of a structure. And if that house is built out of SIPs, you need to know how that system is affecting all the other systems. How did building science come to be? Well, I think it's a little bit to do with the idea of unintended consequences. We don't build houses like we used to. We used to start out by living in caves. There wasn't a whole lot of need for building science because there wasn't a whole lot of system thinking back then. But the design and the construction and the techniques used to build houses and structures today is vastly improved. And as we've done this, we've started to make houses differently and perform differently. And the law of unintended consequences would say we tried to make things better and unknowingly we weren't paying attention to another subsystem and bad things started to happen. And this was noticed as well in the SIP industry when we started building houses really tight and some things didn't working right. And we had to figure out why. In fact, it happens with all kinds of houses that were built tighter and more energy efficient. It was a result of the cost of energy going up. People wanted to build tighter houses. We don't live in stone castles anymore. We have to live in a house that we have to heat, and we have to be able to afford to heat that house. And so a lot of us branched out on our own to try to make houses more tight, energy efficient, and those unintended consequences started coming up, which all of a sudden we realized, hey, what's going on? We have too much humidity, we don't have enough air change, we don't have enough ventilation, and bad things started to happen. So that was really the emergence of building science, is to start to look at these systems and how they relate to one another. We certainly don't build houses like we used to. Now, what is building science going to do for you? Well, it's going to teach you. And most importantly, it's going to teach you how to prevent bad things happening. Bad things in really tight houses, especially SIP houses, can be seen in things that look like this. Things that involve moisture accumulating where you don't want it to accumulate. Dew points happening where they shouldn't happen. Things where structures can't dry out. We don't have enough ventilation to dry them out. We're not promoting drying. And it's these types of things that when they happen and you haven't paid attention to good building science, this is the kind of stuff that can potentially happen. Doesn't have to happen. All you got to do is follow a couple of simple rules. Now in this hour, we're going to follow the parameters of study. I'm going to talk about basically 4 things. I want to talk about heat. I want to talk about vapor. I want to talk about air. And we're going to talk about bulk water. They're all very different items, and they have different levels of importance, and they have different levels of regulation. Actually, the way I've listed these, I've listed them from, in my opinion, least important to most important. Heat transfer, or heat itself, is really probably the least important, and the one that's the most important is water. because water is what destroys houses. And if we have bulk water leaking into our house, as you probably know, it doesn't take too long for a leaky roof to wreak havoc on your house. Air is the second most important in my opinion because it has as much or more to do with energy efficiency of a house than anything else. And it's the SIPs that, when properly installed, stop that air movement and we get good efficiency. And that's really, really important. Vapor, water vapor, we're also going to touch on because it slowly creeps around and causes bad things to happen if we're not paying attention. But first and foremost, let's talk about water. And I'm talking about bulk water. I'm talking about the kind of water that comes out of the ground or falls out of the sky. And it's that water that we want to do what Joe says is the 3D water management system. And that 3D water management systems mean we're going to drain, we're going to deflect, and we're going to dry. Things can get wet and things can dry out. But what we want to do is we want to promote in everything we do in a structure to shed water. We want to shingle everything with the proper flashing, the proper layering of everything so that water has the ability to dry, to fall off, down, and away from the structure. That's the quickest possible way we can get rid of all of that bulk water that we just don't want sitting around or especially leaking into our house. Now, I like to say there's 3 rules of bulk water. And the first one is design the water to keep it out. The second one is design the water to get out if it gets in. And of course, the third rule is kind of the spoiler, and that is it always gets in. Water will always get in, whether in the form of bulk water or even in the form of vapor that then condenses and becomes bulk water. But water will get in. It's as important or more important for you to think about a strategy to let water out, to let moisture out so that the assembly or the components can dry, as it is to think about how to keep water out. Because it's going to get you. It's going to find a way in. And when it finds a way in, if you've trapped it in there and it can't dry out, bad things could potentially happen. When we start talking about this building science and wetting and things getting wet and things drying, this is a good example of showing how we maintain that delicate balance. And that delicate balance is that things can get wet and then they can dry out. Water can keep falling and keep accumulating, but as long as it keeps drying back out, we don't get that point of wetting exceeding the rate of drying. When that rate happens, we get out of balance and we tip out of whack. You'll see also on this demonstration photo that we have what's known as a safe storage capacity. Every item, every component has the ability to get wet and hold a certain amount of water. In some cases, it's a very, very small amount. In some cases, it's a whole lot of water, like a sponge. It has a high capacity to hold a lot of water. OSB has the ability to hold a certain amount of water, as does the foam that makes up SIPs. The point is we don't want that rate of wetting to exceed the rate of drying and exceed its ability to hold that moisture in storage, because once we exceed that, we've tipped the balance and bad things start to happen. And that comes in the form of mold or mildew or rot and things of that nature. And those are the things we don't want. Now, moisture can migrate through a structure in many different ways and formats, known as moisture migration. We can talk about bulk water, and actually we can talk about it in different forms, because water comes in different forms. It can be a liquid, it can be a solid, and it can be a gas. When it's a gas, it's actually a vapor. Vapor can move through the structure in different ways, just as bulk water can move through the structure in different ways. Bulk water, when it falls in the form of rain, is going to find a way, a path of least resistance, and hopefully drain away because you've used the 3D management strategy to deflect and drain and dry the system out. If the water turns to vapor and it becomes a gas on us, it can move in 2 different ways. It can move via diffusion, or it can move through air transport. One moves a lot more water than the other, and we'll talk about that a little later. Vapor diffusion is basically the ability for moisture to move through a material, through an OSB skin, through foam, or through the entire panel. It has a defined amount of permeability that defines the capacity for vapor to move through that product. In air transport, we're not having to move through anything. It's just going along merrily for the ride as air moves through your structure. And we can move a lot of moisture through a hole in our SIP envelope in the form of vapor, which brings a lot of moisture into a structure that we may not want. important to understand. Now, air movement basically, in my mind, equates to air leakage. And air leakage means you didn't do the job that you should have done in making sure you got a nice airtight envelope. We don't want air leakage or air movement because that air leakage robs us of our energy efficiency. It's going to affect that occupant comfort level because, again, it can bring humidity or bring in cold air that we don't want or hot air that we don't want, as well as it affects that humidity level. All bad things happen when we haven't sealed our system properly, and therefore we've got air movement where we don't want. Let's look at a couple of photos of examples of how it is that we've got air moving through a panel. Here you can see daylight streaming through this joint. You can even see a semblance of sealant or mastic that was put in the joint with the attempt to try to seal that joint, but they didn't quite do it. And because they've got that opening, you've got a lot of air moving through here. Again, the mastic is strained to the point of tearing or pulling apart, so we don't have a good tight joint, and that's just a highway for air to go flowing on down through. If you ever want to see air move through a house, just go into a stick frame structure that's been insulated with fiberglass insulation. You can see all around the floor cubbies where air can move freely and move just as freely right through the fiberglass insulation because it doesn't stop air movement. Now there's another thing that forces air to move in and through our structure, and that is the pressures that are exerted on the building when different things are happening. First, there's the wind effect. The wind blows. When the wind blows, we have the windward side of a building. We have a leeward side of the building. On one side, you're going to get a positive air pressure, and the other, you get a negative air pressure. It's this wind effect that causes different forces to either push air into your structure or suck air out of the structure. Next is the stack effect. The stack effect is often misunderstood, but what it is it's basically the buoyancy of heated air that rises up. And as it rises up, it increases the air pressure in the upper level of the structure and decreases the pressure in the lower level. So in essence, what you have is the same effect as wind-driven pressure, or wind blowing against the structure. You have pressure at the top and a vacuum at the bottom, and that's going to draw air in at the bottom and it's going to force air out at the top. We're making this air move where we may not want it to move because of this stack effect. And the worst thing the stack effect will do is it'll start bringing moisture and humidity and air out of the ground if we don't have that properly sealed. The last is combustion and ventilation effect. If we've got combustion going on inside of the house in the form of a fireplace or a wood stove or some improperly vented sealed combustion unit like a water heater, we have air that's coming in and going out where we don't want it to happen. Not something that you want to take, that you want happening in your structure. In the stack effect, I've described how it works, and there's a big reason we care. The reason we care is because it's going to move air where we don't want, but most importantly, it has to do with the crawl space or the basement. When you have that negative pressure down there in that lowest floor of your structure, and it goes into a negative pressure, it's going to pull that stuff in through the walls or up through the floor. That's why we want to have the proper barrier on bottom of the floor, below the slab, or if it's a crawl space, to make sure we have a complete air barrier down there to prevent any of that moisture from moving up through. If you have stack effect in your structure, which you can and will, it's going to attack the weaknesses of your ceiling, and it's going to make that air move through your system where you don't want it to move. All right, let's talk about barriers and retarders. We can have air barriers and we can have vapor retarders. We know that a panel is referred to as a vapor retarder. It retards the movement of that vapor. The barrier stops all air. It's a piece of plastic, a piece of rubber. Nothing can move through it, okay? We're stopping that air completely. It's important to understand why one works differently than the other. What's most important to understand is that we don't use a vapor barrier on both sides or an air barrier on both sides of our SIP panel. We always want to have our assembly designed so that it has the capacity to dry in one direction or the other. Again, remember what we talked about. It's just as important, if not more important, for having a system for the assembly to dry, for the water to get out. And it's that capacity to dry which has to go in one direction or the other, or you're going to have problems. If we put a seam tape on both sides of the panel at those joints, because we're thinking tighter is better and we're going to seal it up with more and more tape, we have maybe caused ourselves a problem. We'll have to define which direction we want it to dry. If we're building in the deep south, where we've got a really hot, humid climate, we can put that tape on the outside of our SIP panel, knowing that the capacity of the panel has the ability to dry to the inside. If we're building in the northern climates, it's exactly the opposite. If we want to put a SIP tape, which is going to be that air barrier at the joints, we always want to put it on the inside so that the panel has the capacity to dry to the outside. We're preventing that air from leaking into the joint and coming in contact with that cold skin on the outside, because that's condensation. That's a dew point, and we don't want to have that. So we're adding that extra layer of protection, which is air sealing, on either the inside or the outside. Well, what if we're building in a mixed climate where it gets hot and cold? Well, then the perfect location is to put that barrier in the middle of the panel. Well, you can't use tape in the middle of the panel, so it falls to you to make the joint perfect. But the common belief now is that in the mixed climates, we still want to dry to the outside, so we're always going to put the SIP tape to the inside of the panel. Again, it's a climate issue. You need to think about where you're building your structure to know which direction this thing is going to dry. But the last thing you ever want to do is do it on both sides. For instance, if you're putting a roof panel package up, you certainly don't want to put a SIP tape on the underside of the panel and then put an ice and water shield continuous membrane roof on the top side. You've created a double barrier. If water leaks in there, and my rule is it'll always leak in somewhere somehow, it can't get out because you've put a barrier on both sides. Don't make that mistake. Now, we talked a little bit about air diffusion, or water vapor diffusing either through a material or air transfer. In air transfer, it's important to understand how much more moisture can move or how much water can accumulate when you're dealing with air transported or air leakage. If you look at this, it'll show that a 4x8 sheet of gypsum board with the interior temperature at 70 degrees Fahrenheit and 40% relative humidity, the diffusion of vapor through that 4x8 sheet of gypsum is only going to yield about 1/3 of a quart of water. That's not a lot of water. Matter of fact, that amount of water may not be enough to exceed the storage capacity of the material, and it may have the ability to dry out accordingly. Okay? If we look at the 1 square inch hole in that same sheet of gypsum, in the same period of time, we can get 30 quarts of water. That's a huge amount of water that's going to likely overtake your strategy for controlling humidity inside the house. And it's that key point that you need to start thinking about. If you've got a hole in your system and you haven't sealed properly, or somebody like a tradesman hasn't done something that they're supposed to and leaves a 1 square inch hole in your system, it's that amount of water that can come into the house. And it's that water that's going to bite you when it comes to the proper performance of the entire system. Next, I want to talk about heat transfer, or just plain heat. Heat can move in a couple of different ways, 3 to be exact. We've got conduction, convection, and radiation. This illustration very clearly shows that if we have a fire on the ground and we put our hands over top of that fire, we feel convection. Okay, and a lot of people think, well, heat rises. That's not exactly true. Heat doesn't necessarily rise. Warm air rises. What heat does is goes from hot to cold. Okay, hot to cold. So if you're standing next to a cold wall, the heat goes out of your body into that cold wall, and that's a movement horizontally, but it's heat moving in horizontally nonetheless. So convection, remember, heat's from hot to cold. If you get convection looping, you've got warm air, which is more buoyant, and buoyant air rises to the surface, and that's where you feel that convection. That's convection heating. The poker that you see sticking into the fire, that's conduction. You're heating up one end of a piece of metal, and that heat transfers up the metal until it gets to the other end and you start to feel it. Okay, there's conduction. The last one is radiation. The radiation is what you feel from the sun. You feel the radiation of the heat of that sun, okay? Those are three different forms, and you need to be able to identify what they are and how they can work against you. If we look at this chart, you're going to see, or this slide, you're going to see a frame wall versus a SIP wall. In the frame wall, air leakage has the ability to move inside of this wall, which is basically an open assembly. And if it's a fiberglass insulation, we have what's known as convection looping. This is a form of heat transfer. It's that convection looping where hot air against the inside skin rises up, comes in contact with the cold skin, and drops back down. Now you've got this cycle of hot and cold moving through the inside of this wall assembly. If we look over to the right side at the SIP structure, or the SIP sample, airflow can't get in there. We can't get any convection looping, and therefore we can't have any moisture moving into the assembly because it doesn't have the ability to transfer any vapor if there is no leakage rate. It's very important to understand. There are certain areas of concern. We'll call these areas of concern the joints of the panels and the joints of the planes. Again, the panel is darn near perfect. We've already described what it is and how it works. It's always going to be these joints and the connections of the planes that you as the installer need to pay extra attention to make sure that none of that air can move in there and take any of that vapor with it and have bad things. Okay, we don't want to hear about a dew point inside of your wall because air carrying moisture went through it. Condensation. Condensation can form in a couple of different ways. First and foremost, if we have a thermal bridge, if we have an air leak like we talked about. It's these thermal voids and bridges that we're most concerned about because of the potential of this dew point. There's different types of components that can create a thermal bridge. Most obviously, it's going to be a solid piece of lumber or even metal inside of our SIP component because that bridge is got a conductivity rating such that the heat can move through it much quicker. And as it can move through it quicker, so can the cold. And when the cold moves through it and you get a cold spot in your wall, you have the potential for that dew point. One of the things that we use very, very effectively is thermography, or the thermal imaging camera. If we take a thermal imaging camera, as you see at these slides, you can see how we can identify things like on the left, which is a void. Somebody just forgot to put some insulation up in the ceiling of that room. Or to the right side, you're looking at thermal bridges. We're got a whole bunch of stud walls in that stick frame house right there, and you can see the heat moving through that wall. It's this thermal imagery that is a great diagnostic tool to allow us to determine where we might have a problem with the building. And when you combine this with the blower door test, where we put a vacuum in the structure and then we suck air through, which might be at a higher or a lower temperature, the combination of the blower door test as well as the thermal imaging really allows us to diagnose how that building is performing. This kind of imagery that allows us to make things very tight. Now when we talk about thermal voids, this is the worst case of a thermal void. This is a SIP panel that's being put together with a block spline, and the installer didn't do a very good job at determining how tight this spline should go into this joint. Look at the amount of air movement that potentially we have going around this spline. You've got a perfectly good system poorly installed, doesn't make it work. The mastic that you see in the joint isn't sealing anything to anything, and you've got a huge ability for air to move through that system. In anybody's book, this is a bad install. Here's something that has the potential for allowing air movement or creating a thermal void, and that is a butt joint. The butt joints of jumbo panels that are made up of EPS foam, when they're not put together tightly, have a little crack. Hopefully this is held together nice and tightly. When some of the newer automated machinery that's used to manufacture panels, we typically don't see something like this. But in some of the plants where you might not have all of the automated techniques or just a breakdown in quality control, as we know happens, you might get something like this where the foam isn't held tightly together and you've got a thermal void. It's important for you as the installer to be able to look at that and identify it as a problem immediately. You have to seal it, fix it, label it, identify it, and get it into the system so that it's not going to become the thermal void that it is here. This picture shows us two things. It shows us a thermal bridge and a thermal void side by side. And they couldn't have messed this one up any worse. It's a single piece of lumber joint, which is right at the joint of the panel. Well, that's our thermal bridge. But right next to it, the foam was cut back too far, so now we have a thermal void. We've got no insulation in one spot because it's just air, and in the other area we've got solid wood. Now I understand you can't get rid of all of the wood or all of the studs inside of a SIP envelope, but we do want to reduce it as much as possible, because when we know what it does to us in a negative way, we as designers want to work that much harder to get as much of the lumber out of the SIP structure as possible. It's very important. Here's some imagery that you'll see that, again, it identifies where those studs are and shows how on the left side you can see the conductivity of that stud, where the heat is coming through the wall and that cold air is moving through there quite quickly. You can identify things like this as air leakage very, very quickly. Now, if we take building science back down into the crawl space, and we in fact are in an uninsulated crawl space, and if we've got dirt floors and we don't have vapor barriers, and we have what that stack effect was we talked about before, we have a recipe for disaster, because we're pulling, again, more moist air inside of our structure that we don't want. So just as bad things can happen in a crawl space, bad things can also happen in the attic. There's different ways to look at attics. We can have ventilated attics or unventilated attics. Unventilated attics might often be referred to as conditioned attics. Some people might unknowingly refer to these conditioned attics as hot roofs. And that would imply that because we have taken insulation and moved it up into the top of the roof assembly so that our attic is completely conditioned, we've got a hot roof. That's not exactly true. We'll talk about that in a minute. First, let's talk about why we might not want to have a ventilated attic. Well, we don't want to have a ventilated attic because, one thing, it gives us more livable space, but more importantly, it allows us to take things like ductwork and our HVAC system and move them into an area where we don't have that huge differential in temperature. If we have a conditioned space, again, we don't need to worry about things like leaking ductwork. So these are the type of things that give us a huge advantage when building with SIPs. The SIP panel takes the insulation out of the ceiling and moves it up into the roof line. And this can be a really good thing for us in a lot of different areas. In cold climates, the cold roof surface is sometimes used to control ice dams. And we do that with a ventilated layer over top of the roof to maintain that cold layer. And that's where the misnomer of hot and cold started to come into play. People thought that when you put the panels up there, you were going to get a hot roof, and somehow that translated to shingle warranty issues and you were going to degrade your roof system. And it's just really not that true. The reason we ventilate a roof assembly, not ventilate the attic, but ventilate a roof assembly, is because we're trying to promote drying. It's a wet-dry issue, not a hot-cold issue. So it gets a little confusing, but you have to understand we've got two areas where we're talking about potentially ventilating. One is the attic itself, which could be ventilated or unventilated, and with a SIP roof, it's going to be unventilated because it's now conditioned space. And then on top of the roof, we can ventilate the roofing assembly or back ventilate the roofing material, if you will. So there's two different areas of ventilation, and you have to keep the two separated. If we go back to the conventionally vented attic space, as it shows on this drawing, we have things like our air handler up in the attic. It's up there with the ductwork going around, and we have the sun beating down on the roof. How hot does it get in attics in the middle of the summertime? A lot of people won't even go in their attics in the middle of the summertime, in the middle of the day, because it's just too hot. And we've put our ductwork up there trying to force air that is conditioned, that we pay for, to either heat or cool in that inhospitable environment. It just doesn't make a lot of sense. It's a bad thing to do. And then you start having all of these things like duct leakage, and again, it's just like throwing money out the door. Now, if we use the SIP envelope and we go to that unvented, conditioned attic, we no longer have to worry about that tremendous temperature differential. In some areas in the Southwest, where you're actually in a desert climate, if you have a vented attic, it's a little bit like living underneath a broiler. When the temperature up in your attic reaches 140 or 150 degrees and you're trying to be comfortable in the living space right below that, at down around 68 to 72 degrees, it's like living underneath a broiler. We want to get away from that scenario. We want to get that SIP envelope up there so that we can prevent that radiant heat from coming through the ceiling, and we cool the whole environment down. We don't have that huge fluctuation of temperature. We're living underneath that broiler, as I like to say. This is a good example or a picture of showing the difference between heat loss and the convective nature of heat inside of your building in the difference between a conventionally framed attic and a SIP conditioned attic. This picture, the SIPs are obviously on the left, and you can see the snow hasn't melted at all. And if you look over to the right, you can see where it's completely melted away. The difference in heat, with the inside temperatures being exactly the same, shows how these different systems perform. Now, have you ever had somebody say to you, you can't build houses too tight because a house has to breathe? Well, nothing could be further from the truth. Of course, you can't build a house too tight. You can only not ventilate it right. We don't build houses the way we used to, and we ought to be glad that we don't. When we built houses the way we used to, they were leaky, which from a building science perspective may have been good in the sense that it could dry itself out. And then once we put a lot of insulation in there, it couldn't dry itself out as well. But with the proper moisture controls, the bulk water flashing controls, we've designed a system that has the ability to have a means to dry out. And more importantly, we can build it really, really tight, and we can control the ventilation. We can control the air that moves in and out of this structure, because that's what we really want to do from a building science perspective. These are the ventilation strategies, and we're going to talk a lot more about this when we get to Chapter 8. But just to touch on them briefly, these ventilation strategies are all geographically dependent. We have to know what air we're bringing in, how much air we're bringing in, and that air that we do bring in and we filter and we dehumidify improves the indoor air quality of the living environment. Obviously, we want a good indoor air quality living environment. And this ventilation strategy has a balance between supply and exhaust air. We need to understand how all that works together. Most importantly, when you're dealing with that HVAC contractor, remind him that he's got a V stenciled on the side of his van. He also has to work with ventilation, and there needs to be a strategy to bring that air into the house. Now, when we talk about ventilation, there's another type of venting. It's sometimes referred to as back venting, or as I said before earlier, up on the roof, we can ventilate the roofing material. We can back ventilate that as well. Now, why do we want to do back ventilating? Where do we do it, and how do we do it? Well, where we should do it is where we have a concern about moisture. This is where I have a difference of opinion when people refer to a SIP roof as a hot roof. If it was a hot roof and we went to ventilate it to make it cold, that's really not why we do it. We ventilate that roof up on top so that we can get more airflow, so that we can increase the capacity for that assembly to dry out. So where do we do this? Well, typically we do where we have cold, wet, long, cold, dark, wet nights, areas where the rainfall exceeds the capacity for the structure to be able to stay dry and stay durable. So in the far north, in the areas where we have a lot of rainfall, both siding and roofing should be back ventilated. Now, he typically doesn't refer to his roofing as back ventilated, it's ventilated, and the siding is back ventilated. But what we're doing is we're giving a space for air to move behind this covering, this blanket or shell around our SIP envelope, so that we can increase the capacity for that thing to dry. Now, how do we do it? Well, there's different ways to do it. If we're working in walls, we can simply frame out, stud out, fur out the siding. Depending upon what type of siding, though, we may not need to do it. The one type of siding that we don't need to fur out or we don't need to back ventilate are the sidings that are self-ventilating. And what are those? Vinyl siding. If we have a siding that doesn't have the capacity to dry out, then we need to bring it off of the wall and give it a little bit of air movement behind it. We need to make a disconnect between the siding itself and the building. And in between that as well, we need a drainage plane. What's a drainage plane? It is either going to be the felt or the house wrap that directs the water down and away from the SIP when the siding leaks. And you know that sidings leak always. We can always know that siding, every type of siding is always going to leak, and that's important. If you understand that it's going to leak, plan for it, allow for it. Know that you need to have a proper drainage plane behind it so that it can take it away, all right? Also, you need to be aware of some types of sidings which are known as reservoir claddings. What's a reservoir cladding? That might be a masonry or brick, block, stone, something of that type that has the capacity to hold a lot of water. Next thing, we're going to go from the cladding, which we back ventilated. I want to get up on top of the roof where we talked about ventilating the SIP roof. Remember, I'm ventilating the SIP roof because of not heat. I'm ventilating it because of moisture. And the same thing applies to cladding as it does to roofing. Okay, if we're in an area where we have a lot of rainfall, darkness, cold, long nights, cold areas, that's the area where we want to ventilate our roofing. We want to do it for the sake of durability, if nothing else. Because if the roof gets wet and it continues to get wet and can't dry out, then the rate of wetting has exceeded the rate of drying. And that's the number one building no-no. Because now we have bulk water, which is going to start tearing up our building. It will destroy SIPs if they get wet and stay wet, any type of SIP. It's going to absorb that water and we're going to have a problem. That's why we're going to do that back ventilating. This diagram shows the venting coming through the fascia. We fur that roofing up, and we can either put a whole nother layer of sheathing on top of furring to give us that space, or we can use simply strips, or in some cases we can use a polypropylene mesh. A polypropylene mesh, also known as cedar breather, also they've used that material for cedar shingles that can be used on roofing, and it holds the material away from the SIP and gives the area for air to move underneath. If we're putting metal roofs on, one of the tricks we'll use is diagonal lath. And that diagonal lath is laid on top of the felt paper so that we have that air movement, and because of the vertically laid standing seam metal roof or crimp metal roofing, we now have those diagonal laths to attach to every 12 or 16 inches or whatever the fastening requirement is. Again, we're ventilating that roof assembly. Now, what happens when we do all of these things properly? If we pay attention to the rules of building science, if we understand heat and air and vapor and how they move through our assembly, well, if we've done all the things that we're supposed to do, then our building is going to perform properly. You're going to have better indoor air quality. You're going to have more comfort from the occupants inside the building. The health of not only the building but the occupants themselves is going to increase. Most importantly, durability, and along with durability comes affordability, and that means we're not losing a lot of energy to our structure. Now, I want you to pay particular attention to where all of this information came from. It came from the Builder's Guide to Structural Insulated Panels, and this book is available to you through the SIPA main office. I encourage you, if you do not yet have a copy, is to get that book and read it. Read the whole book and read it 2 or 3 times. It'll take a while to grasp all the things about building science that really can affect the way that you build with SIPs. In addition, Green Builder College gives you the opportunity to learn a great deal more about building science through their Houses That Work program, which is taught by Mark Liberté. He is an instructor that knows so much about building science and has a course that goes into far greater detail than I've gone into here in less than an hour. He is a great instructor. The course is available on Green Builder College, and I highly encourage you to take the time, invest the money and the time to learn more about building science on Green Builder College. We'll see you at the next chapter.